So pyrazine, it is the third diazine. So far we have seen pyridazine and pyrimidine. Now let us see about the pyrazine. So pyrazine is a 1,4-diazine and it is a symmetrical molecule. The two hydrogens occupy position 1 and 4. So pyrazine occurs naturally as several of its polycyclic derivatives. The pyrazine occurs naturally, though not in appreciable amounts, but several polycyclic derivatives of pyrazine ring system, such as pyridine and phenazine. So pyrazine occurs as its derivatives rather than free. The pyrazines have long been of interest to medicinal chemists. Pyrazine has been an interest to the medicinal chemists. Their derivatives, many of which are natural products, have proven to be useful as antibiotics, diuretics, and anti-tumor agents. So many of the derivatives of pyrazine possess activities like antibiotic activity, diuretic activity, and anti-tumor activity. This is a dibenzopyrazine. This is a dibenzopyrazine. So various dihydro and tetrahydropyrazines are known, but most important is hexahydropyrazine or piperazine. Hexahydropyrazine is called piperazine. This is the structure of piperazine. So coming to some of the physical properties of the pyrazine. Pyrazine is a colorless solid having melting point 54 degrees centigrade. It is a weaker base compared with pyridazine and pyrimidine. So the reasons are not known for its decreased basicity. So pyrazine may be represented as a resonance hybrid of number of canonical structures. The resonance energy has been calculated to be 24.3 kilocalories per mole. This is mole, not more. It is kilocalories per mole. It has a dipole moment of 0. It is a symmetrical molecule and it has 0 dipole moment. The pi electron density data indicate that increase in pi electron density at the nitrogen atoms and a depletion of pi electron density at the carbon atoms. The electrons, the nitrogen atoms that are present in pyrazine are electron withdrawing in nature. Therefore, the carbon atoms will become electron deficient, pi electron deficient, whereas the nitrogen atoms become pi electron rich. These are some resonance structures of pyrazine. So this is the structures with the change in the position of the double bonds. The second structure is written, and when these pi electrons are withdrawn by nitrogen, we get negative charge and positive charge here. Similarly, on the other side, when these electrons are donated to nitrogen, we get plus charge here and minus charge on nitrogen, and so on. We can write so many resonating structures for pyrazine. So coming to methods of synthesis. So reaction of 1,2-diketones with 1,2-diamides. So 1,2-diketones undergo condensation with 1,2-diamides to form an intermediate dihydropyrazine, which on subsequent dehydrogenation gives pyrazine. So it is a general method with which we can prepare various alkyl or aryl alkyl substituted pyrazines. We can vary the R. These two are with the two alkyl groups, two aryl groups, or one alkyl and one aryl group. So they condense. The amino group condense with C double bond O. Here also the amino group condense with C double bond O to form a dihydro derivative. We get a dihydro derivative which on dehydrogenation gives a substituted pyrazine. This is the first method. So reaction of 1 2 diketones with 1 2 diamines results a compound which on dehydrogenation gives pyrazines. The second method is from alpha amino carbonyl compounds. So this method involves a self-conjugation of two molecules of alpha amino carbonyl compounds to form 2,5-dihydropyrazine, which on oxidation gives pyrazine derivatives. The alpha amino carbonyl compounds used in this reaction have been obtained by nitrogenation of ketones, followed by reduction of the amino ketone. So it is a nitroso compound. The nitroso compound is reduced with the stannous chloride to the corresponding amine. So the amine is then treated with a base. So two molecules of alpha amino ketones. This is one molecule and this is another molecule. So nitroso compound is reduced to amino compound. The two amino compounds, these two are amino compounds which will undergo conjugation to form a dihydropyrazine, which on oxidation gives a substituted pyrazine. So similarly, alpha amino acids and their esters normally undergo dimerization to the corresponding 2,5-dioxopyrazines, which can be alkylated with triethyl oxonium chloroborate. So the derivative diethoxy the resulting derivative is converted into pyrazine by oxidation with DDQ to form pyrazine. These are amino acids. So alpha amino acids, two alpha amino acids. So condensing to form an intermediate, so which is then converted to another intermediate. So this intermediate on oxidation with DDQ gives a substituted pyrazine. Next, the third method is from azines. So irradiation of diphenylazine yields 2, 3, 4, 5 tetraphenylpyrazine on rearrangement. So other products have also been obtained. The compound is irradiated with UV light. It forms an intermediate, which then undergo reaction with another molecule of this diphenylazine to form an intermediate, which will rearrange to a 2, 3, 5, 6, 2, 3, 5, 6 tetraphenylpyrazine. a photochemical method from diphenyl azurine. These are some of the methods of preparing pyrazines. So coming to the chemical reactions, pyrazines are aromatic in nature, and the main features of their reactions may be interpreted by regarding them as pyridines into which a nitrogen atom has been introduced at the para position. So they resemble pyridine in their reactions. Pyrazines behaves as aromatic compounds and resemble pyridine in their reactivity. So in pyrazine, there is an additional nitrogen atom at the fourth position. Both nitrogen atoms in pyrazine behave as the pyridine type of nitrogens. So pyrazine undergoes protonation at only one of the two carbon atoms. So it undergoes monoprotonation at one of the two carbon atoms, and deprotonation can be done by using strong acid. The first one is reaction with acid. So one of the two nitrogen atoms is only protonated. It can form only monoprotonated compound. So electrophilic substitutions. The presence of two nitrogen atoms deactivates the ring towards electrophilic attack. As the other diazines, pyrazines also do not easily undergo electrophilic substitutions. So if electron donating groups are present, then electrophilic substitution is possible. So it is known that chlorination of 2-methyl-pyrazine under mild conditions gives 3-chloro-2-methyl-pyrazine. It is the mechanism of the reaction involves an addition-elimination reaction. So nitration reaction is not possible on substituted pyrazines. So pyrazine, if it is unsubstituted, it do not undergo electrophilic substitution reactions. However, if electron releasing groups are present in the ring, then they can undergo certain electrophilic substitution reactions. So these electron releasing groups makes these carbon atoms electron rich. Hence, they can undergo some electrophilic substitution reactions. So for example, this 2-methyl-pyrazine on chlorination gives 2-methyl-3-chloro-pyrazine. However, nitration is not known. So reaction with nucleophilic reagents. So pyrazine ring is electron deficient. So pyrazine reacts in a manner similar to pyridine in the Chichi-Babin reaction. So pyrazine on treatment with sodium azide, it forms the 2-amino-pyrazine. So 2-fluoropyrazine undergoes a reaction with sodium azide to give 2-azidopyrazine, which exists in dynamic equilibrium with the tetrazool 1,5-A pyrazine. So it is undergoing some cyclization. The resulting diazide, when this 2-fluoropyrazine is treated with sodium azide, it forms a 2-azidopyrazine, so which undergo rearrangement. It is undergoing a cyclization. The azide is forming a ring with one of the the nitrogen atom present ortho to the azide. Because of the inductive and resonance effects of the nitrogen atoms, protons attached to the alpha or beta methyl carbon atoms are acidic and are easily removed by strong bases. So the resultant carbanions undergo condensation and alkylation reactions. For example, 2-methyl-pyrazine. 2-methyl-pyrazine. So these two nitrogen atoms are electron withdrawing in nature. Because of the electron withdrawing nature of these nitrogen atoms, this methyl group can easily lose H plus when treated with a strong base to form a carbanion. This carbanion can undergo condensation reactions or alkylation reaction. The carbanion here adds to this R plus. This R plus to form a alkylated derivative. So therefore, these hydrogen atoms will become acidic because of the presence of two electron withdrawing nitrogen atoms in the pyrazine ring system. So reaction with oxidizing reagent. Next, reaction with oxidizing reagent. So as the other diazines, pyrazine ring system is stable to the action of oxidizing reagent. So we have seen the other diazines, pyridazine and pyrimidine. They are also stable to oxidation and forms N oxides when treated with oxidizing reagents such as hydrogen peroxide. So coming to the pyrazine, it is also stable to the oxidizing reagents. However, the alkyl groups present in the ring can be oxidized to the corresponding carboxylic group, and pyrazine forms a dianoxide when treated with trichloroacetic acid. So N-oxide formation of substituted pyrazines with hydrogen peroxide and acetic acid or pyracids takes place on the most basic and least sterically hindered nitrogen. When the two nitrogen atoms are different, that is, when there are varying substituents in the pyrazine ring system, the least hindered nitrogen atom can only form N-oxides on oxidation with hydrogen peroxide. So here we can see the 2-chloropyrazine. There is a substituent here. Therefore, this nitrogen is hindered and this is not hindered. Therefore, N-oxide is formed by the least hindered nitrogen atom of the pyrazine ring system. Similarly, if there is any alkyl group in the pyrazine ring system, it is forming here. In this case, it is forming N-oxide. N-oxide is formed by this nitrogen atom and not this nitrogen atom as in the other case. In the first case, N-oxide is formed by this nitrogen, whereas in this 2-methyl-pyrazine, N-oxide is formed by the first nitrogen atom. So 2-chloropyrazine yields 4 N-oxide, while a mixture of N-oxide is obtained from 2,5-dimethyl-pyrazine. If there are two methyl groups, then we get a mixture of the dioxides. Oxidation of 2-chloropyrazine, on the other hand, takes place at the nitrogen atom adjacent to the chloro group with ferrous acid, that is peroxysulfuric acid in concentrated sulfuric acid. So N-oxide formation depends upon the substituents which are present in the pyrazine ring and the action of the reagent. In the first case, we have seen 2-chloropyrazine forming N-oxide at the fourth nitrogen atom. Whereas in this case, when we change the reagent, this 2-chloropyrazine N-oxide is obtained. So with sodium perborate, a mixture of N-oxides is obtained. So here it is a mono N-oxide and it is a di-N-oxide. There must be a methyl group here. There must be a methyl group present in this position, which is not written here. And along with this, we are also getting a other product. So besides chemical oxidation, pyrazine can also undergo enzymatic oxidation. The enzymatic method of oxidation of methyl groups or aromatic heterocycles is a technique for the preparation of heteroaromatic carboxylic acids. Certain enzymes which have been used in the oxidation are Pseudomonas, PD, PDDA, ATCC 33015. So this is a dimethyl pyrazine undergoing oxidation when treated with Pseudomonas. These are other examples. So this is an N-oxide when treated with the acetic anhydride, it forms 4-methyl 6-pyrazinone. So a different product is obtained when there is a change in the position of the methyl group. By treatment with same reagent, it is forming 2-hydroxymethyl pyrazine. This is a reaction that involves the formation of 2,3-pyrazine. So pyrazine 2,3, this is pyrazine 2,3-dicarboxylic anhydride. So on pyrolysis, on heating, it forms a intermediate. So, which results in the formation of 2-melanonitriles. 2 nitriles. It results in the formation of 2 nitriles. So melanonitrile and fumaronitride. So this probably involves an intermediate dihydroxyazine. So some of these pyrazine forms this dehydroxyazine intermediates. This pyrazine 2,3-dicarboxylic carbohydrates on pyrolysis, it forms a dehydroxyazine intermediate. So that undergoes decomposition to form melanonitrile and fumaronitrile. So this reaction involves the formation of this 2,3-pyrazine as an intermediate. The intermediate formed is a 2,3-pyrazine. The compound is containing a 2,3 triple bond. These are some of the reactions of pyrazine. So it possesses the derivatives of pyrazine possess antibiotic and antidiuretic activities. So some of the pyrazine derivatives also possess anti-tumor activity. This is about the synthesis, reactions and importance of pyrazine.